Now, of course, after all our work with the simultaneous equations, we did say that we would keep an eye out for anywhere where we could use that shortcut, that hack, so to speak. So let's go back up past all of our working out to this line here. This very first line after we had done the multiplication. This works for any value of x. So are there particular values of x we could choose that would make things easier for us? So notice that if we wanted to figure out a first of all, it would be good if we could eliminate b and c with just one appropriate choice of x. And look, they both have an x minus 1 in them, whereas there's no x minus 1 attached to the a. So if we set x equal to 1, let's come off to the side here. If we set x equal to 1, what happens? Well, the 1 minus 1 here and the 1 minus 1 here means that both of these terms just go to 0. And so when we substitute in x equals 1, over here we have 1 plus 1 is 2, and 1 plus 2 is 3. And so we have 6 slots of a equal to 6, and therefore a equals 1. How good's that? And then likewise, if we choose appropriate values of x, again, we can solve for b and for c. So let's take a fresh look at the equation once again. We just want to be left with b, and so we notice that both the a term and the c term have an x plus 1, but the b term doesn't have that. So if we let x equal minus 1, we'll get a minus 1 plus 1 here, we'll get a minus 1 plus 1 here, and so this term will go, this term will go, and that means we can say that 6 is equal to b times negative 1 minus 1, so minus 2, negative 1 plus 2, so 1, and so therefore we can see, alright, minus 2 lots of b is equal to 6. That means b must be negative 3. Once again, like we saw before. Finally, a choice that would get c by itself, we'll notice that c doesn't involve the x plus 2 brackets. So if we let x equal negative 2, we will get this term disappearing, this term disappearing, and we'll be left with c outside of negative 2 minus 1, so minus 3, and negative 2 plus 1, okay, so negative 1, and so therefore we get 3c is equal to 6, or that must mean c is 2. So we can actually figure out these values of a, b, and c in a much quicker way. Okay, we're going to go on to our fourth example now, but it's an incomplete example. Okay, I'm not giving it all to you yet because I want us to think through it a little bit more deeply. But let's read the example. So our original fraction is 4 over x minus 1 times x plus 1 all squared. And so, the example goes, if this can be represented as the sum of some simpler fractions, what are the values of a, b, and c? And I want us to guess as to how we should set this up, just like what we've been doing previously. And one such way might be to think, okay, well, x minus 1, that could be my first fraction, so some unknown numerator over x minus 1. And then x plus 1 all squared, well, that's just x plus 1 times by itself, right? X plus 1 times x plus 1. So maybe I need to set up two fractions. The first one is over x plus 1 here, and then the second is another one over x plus 1. That would seem reasonable, right? But what would the issue with that be? Well, notice that if we were adding all of these together, this second and third fraction already has a common denominator of x plus 1. And so we could just combine these together, couldn't we? So they're in one fraction. But b plus c, well, that's just some constant, so we'll just call it b. But then when we do combine these two fractions together, whatever ends up happening on the numerator, let's not worry about that so much. On the bottom, we're going to get x minus 1 times x plus 1. And that's different to what we started with. So we can't actually set it up like this. We need to do something a little bit different, a little bit trickier. So let's have a look at the proper example now. What we actually need to do is set it up the same as before to start with, but then our third fraction is actually over x plus 1 all squared. So now that we've got our full example, let's go ahead and solve it. And so the first thing we're going to do is multiply both sides by this denominator, x minus 1 times x plus 1 all squared. So on the left hand side we simply get the numerator 4, and let's go through fraction by fraction. So we will have a multiplied by, now the x minus 1 will cancel with this x minus 1, and so we just have x plus 1 all squared. Then we have b, and in this case the x plus 1 on the denominator will cancel with one of these x plus 1s. So we still have this x minus 1, and we just have 1 of the x plus 1s. And then finally with c, the whole x plus 1 all squared cancels, and so we actually just get c times x minus 1. Okay, now this time, instead of going through a full process of equating coefficients and solving simultaneously, let's see if we can use the shortcut method straight away. So what would an appropriate value be to plug in for x that would eliminate 2 of our unknowns? We'll notice that there is an x minus 1 attached to the b and an x minus 1 attached to the c. So if we let x equal 1, then both of these terms will go to 0. So we have 4 on the left hand side equal to a outside of 1 plus 1 all squared, and then this second term goes to 0 and the third term goes to 0. That's why we chose x equals 1. And so when we have 1 plus 1 we get 2, and squaring that gives 4. And so if 4a is equal to 4, a must be equal to 1. So we've figured out a. Okay, let's try and work out our next constant value. What do you notice? Well, hopefully we can see that both the a and the b have an x plus 1 in them. Right, so x plus 1 and x plus 1. So let's set x equal to -1 this time. And so what will that mean? Well, we have 4 on the left. The a term will go to 0. The b term will go to 0. And we are left with just the c term, which is -1 in the brackets, meaning that -2 times c is equal to 4. And so therefore, c must be -2. Okay, so a and c, tick, tick. What about b? Because we notice that it's a little bit like there's no other values, a little bit tricky now, no other values of x to just plug in so that we get b straight away. But since we now know a and c, and remember x can be any value, let's just choose a value of x, preferably one that makes things relatively easy, sub in the values of a and c that we now know, and solve for b. So, values of x such as 0 or something like that would be really good. We don't want to choose 1 or -1, remember, because we've already used them. So let's go with 0. That's a nice one. And let's see what we get. So 4 on the left. When we sub in 0 here, we get 0 plus 1. So that's just 1. And when we square 1, we get 1. So we just have a. Then when we sub in 0 here, we will get 0 take away 1 and 0 plus 1. So overall that becomes -1, and so we get -1 times b. So I might actually change that plus to a minus, so minus b. And finally, same thing, 0 times -1 is -1, and so we get minus c. So we've come up with the expression 4 is equal to a minus b minus c. But we know what a and c are now. A is 1 and c is -2. And so we can solve for b as 1 plus 2, which is 3, take away the 4, and so we get -1. And so we have our three values, a, b, and c. And so we could rewrite our initial question as simpler partial fractions. Alright, so this example has taught us an important rule that we are going to write down. And that is the rule concerning repeated linear factors in the denominator. So I've got our example here that we just talked through to help us understand what this means. Notice that this linear factor, x minus 1, it just occurs once. And so there is only one partial fraction that has x minus 1 in the denominator. But x plus 1, it occurs twice because we have x plus 1 squared. And so it actually corresponds to two of our partial fractions. One where we just have x plus 1, and a second where we have x plus 1 squared. And so we can take this idea and generalize it. For each linear factor, ax plus b, so just really generalizing it, okay, both of these are linear factors. For each linear factor occurring n times, so this linear factor occurred once, this factor occurred twice, and we're just saying if it occurs n times in the denominator of a proper function, then there corresponds, or there's a matching sum of partial fractions of this form. Okay, so of the form, and I want you to keep thinking about this one that we focused on, where it was squared, it occurred 2 times. We're going to see our first fraction with some unknown on the top over our linear fraction. So we're going to see that. Now we would stop there if it just occurred once. Okay, but it doesn't. That's just the first. If it occurs twice, there is a second fraction. Once again, some unknown constant on the top. But then we don't just have ax plus b, we have ax plus b squared on the denominator. Okay, and that's what we saw with our example. The x plus 1 squared, the repeated linear factor, corresponded to 2 fractions. And so if we have n instead of 2, we keep going. Right? We keep going until we get to our nth fraction. Once again, some constant on the top that we'll just call an. But what's on the bottom? Ax plus b to the power of n. So cubed, power of 4, we just keep going. Okay. So this is our general rule. So let's have a go at a question now where we set up the generic partial fractions. So this isn't an example as such. We're not going to go through and completely solve this, but just to see if you understand that general rule we just wrote, how could we decompose this into some partial fractions? So let's focus on our first linear factor, which is x plus 3. And it only occurs once. So we only need to write it once. Right, we don't know what this numerator is, we'll call it a. But what's going to happen with our x minus 1 all cubed? Well, because this is x minus 1, a linear factor, repeated 3 times, we will see it as x minus 1 all squared, and x minus 1 all cubed. And then we can go back and say, well, we've got to figure out the constants b, c, and d. Okay, so that's how we would break a fraction like this, break it up or decompose it into its partial fractions. Okay, the next one though is an example that's a little bit different again to what we've seen. Why is it different? Well, in this case, we have to find a, b, and c such that this original fraction, which contains a quadratic factor in the denominator, can be expressed like this. So when we look at x squared plus 2x plus 4, this is irreducible. We can't factorize this. Right? So we just have to leave our denominator in the second fraction as x squared plus 2x plus 4. But notice that our numerator has a different form now. See, previously we have just had linear factors like this one, and so we can simply have constants above them. But when we have a quadratic denominator, then we need to have a linear numerator. Alright, so let's get into this one and see how it all pans out. And we once again start by multiplying by this denominator. This gives us 5x plus 2 on the left hand side, and then on the right hand side of the equals we get a outside of the x minus 1's cancel, so a is outside of this quadratic, and then bx plus c, well, that will be outside of x minus 1. Option 1 is to expand and equate coefficients. Okay, now like we've seen previously, that usually takes a while. So is there something we could do? Are there some x values we could choose to speed up this process? So what do you notice? Well, the first thing that I notice is that bx plus c, all of this is multiplied by x minus 1. Meaning if we let x equal 1, then this will go to 0, and so this whole term will go to 0, leaving us just with a in our equation. So let's sub in x equals 1. On the left hand side we have 5 lots of 1 plus 2, so that's going to be 7. Let's set that up there. And then on the right hand side we have a outside of x squared, so 1 squared is 1, plus 2 lots of 1 plus 4. And this has all gone to 0. And so 1 plus 2 plus 4, well, that's 7. So 7 lots of a equaling 7 means a is equal to 1. So we've found our first variable, our first unknown, I should say, already. Okay, so what's next? What else do we notice? A little bit hard to eliminate the a variable, isn't it? But that's all right. We don't have to worry about that now because we've already figured out what a is. So let's look back over here and notice that b is attached to x. So if we actually let x equal 0, then b times 0 disappears. So on the left hand side, 5 lots of 0 plus 2. Well, that's just 2, isn't it? And then on the right hand side, okay, we have a outside of 0 squared plus 2 lots of 0 plus 4, so simply 4. Now what happens here? B times 0, that disappears, right? So we just have C multiplied by 0 minus 1, or negative 1. And so therefore 2 is equal to 4a minus c. But we know what a is. A is just 1. And so we can see that c must be 2, right? 4 take away 2 is 2. So we've got a and we've got c. And now we're in a similar position to what we've been previously, where since we know 2 of the unknowns, we can choose any x value now to sub in along with the values of a and c, and we will find b. Now we can't use 0 or 1 because we've already used them, so minus 1 is a nice simple value to use. So what do we get on the left? 5 lots of minus 1 plus 2, so that is negative 3. And this will be equal to a, which is 1, outside of negative 1 squared, so 1, minus 2, 2 lots of minus 1, plus 4. Then we get to this section, and we have negative b, because b is times by minus 1, so negative b, plus c, but that's 2. That needs to be multiplied by x minus 1, so minus 1 is negative 2. Alright, just a little bit of tidying up to do. So in this brackets here, we have 1 take away 2, which is negative 1, but then plus the 4, so that's 3. And expanding over here, we have negative 2 times negative b, so 2b, and negative 2 times 2, so minus 4. Giving ourselves a little bit more room, and finalising our answer. What have we got? We'll get the 2b by itself, and then 3 minus 4 is minus 1, so adding that to the other side we get negative 2, and so we can now see that b is equal to negative 1. So there we go, we have our three values, a equals 1, c equals 2, and b equals negative 1. Now of course we could go through the expanding, equating coefficients, solving simultaneous equations, okay, and it's not too bad, but this is slightly quicker. Alright, the last idea we have to talk about is repeated quadratic factors in the denominator. So we've already dealt with repeated linear factors, and the same idea happens if we have a quadratic factor that repeats. So for example, something like this. We have a linear factor, and there's just one of those. So that is a over x for its partial fraction. But then we have a quadratic factor that repeats twice. Now we saw previously that when we have a quadratic factor, so in this case x squared plus 1, that the numerator must be linear. Okay, so I've already used a, so I'll use b, bx plus c. Okay, but it's repeated, and we use that same rule as before, where we don't just write x squared plus 1 again. That wouldn't help us. We actually need to square it. And so it's still a quadratic denominator, however, so we have another linear. Let's use dx plus e. Follow the alphabet properly. Okay, so we have another linear numerator. So let's do one last example that utilizes this fact. So example 6, express 1 over x times x squared plus 1 all squared, so what we just saw before, as a sum of partial fractions. So we have one linear factor in the denominator and a repeated quadratic factor. So we can say that this is equal to sum a over x, that's the first partial fraction. Then our second partial fraction has x squared plus 1 in its denominator, but because it's quadratic, we need to have a linear numerator. And then we have x squared plus 1 again, but it's all squared. And this will be another linear numerator. So let's go ahead and multiply everything by what we see on the denominator of the original fraction. And so if this is our left hand side, we get 1. And then on our right hand side, we get a outside of x squared plus 1 all squared, because it's just the x's that cancel. Then in our second fraction, we have our bx plus c, and we will be left with an x, so the x will still be there, and an x squared plus 1, so just one of them. Finally, with our third fraction, we have our dx plus e, and it is the x squared plus 1 all squared that cancels, and so it's just this x that remains attached. Now in this case, if we look for a shortcut, we can see that there is one when we set x equal to 0. So x equal to 0 will get rid of this and this. But otherwise, there's not much we can do, because there's nothing we can plug into an x squared plus 1 that will make it go to 0. No real value of x, that is. And so for this one, we will just have to expand it all out and equate coefficients. But luckily, because there's a lot of 0 coefficients, things should work out okay. So let's fly through this. We have a outside of, and we need to expand this, and it's a perfect square. So we have x to the 4 plus 2 lots of x squared plus 1. And then over here, let's start by first just expanding the x with the x squared plus 1. So x cubed plus x. And then this last one, we can distribute the x. So we get dx squared plus ex. Alright, if we keep going, we have ax to the 4. Then we have 2ax squared plus a. And a little bit of work to do. We've got a FOIL to do here, so we get a bx to the 4 plus a bx squared. Now focusing on the inner, we have cx cubed and cx, and then our last two terms remain the same. Okay, now let's collect everything together. So powers of 4, that's a and b as the coefficients. The cubics, well, look, there only ended up being 1, just c. C is the only coefficient of an x cubed. Now on to the x squareds. So we have a 2a here, but we also have a b here and a d. So 2a plus b plus d. In terms of values attached to an x, we just have c and e. Okay, so c and e are attached to an x. And finally, the constant term, there's only one, a. And so when we compare to the left-hand side that just has a constant of 1, that means all of these have to be equal to 0. So a plus b is equal to 0, c is equal to 0, this one's equal to 0, and this one's equal to 0, and a is equal to 1. So I've already got some solutions. We've got a equals 1 and c equals 0. Those two just fall right out. If we consider here, since c is 0, then that means e must be 0. So that's another nice one that just falls right out. A plus b, well, if a is 1, then b must be negative 1 in order for this sum to be 0. And so the only letter we now don't know is D. Here, 2 lots of A, so 2 plus B, so that's -1, so 2 minus 1 is 1. So 1 plus D is equal to 0. So that must mean that D is -1 as well. And so we have our 5 values. So even though we had to expand and equate coefficients, this one was actually kind of nice because of all the zeros. And so there we go. There are the values of A, B, C, D, and E, meaning that we can write our initial fraction as the following sum. So our initial fraction that we started with will be equal to A on X, so 1 on X, plus BX plus C. Well, since C is 0, that's just negative X over X squared plus 1. And then our third fraction was X squared plus 1 all squared, and that was dx plus E. But once again, E is 0, so that's just minus X as well. And so there we go. Alright, that finishes our second video of the partial fractions, so well done. Good luck with the questions.